guys, good to see you again. In this video we will be looking at a pretty important concept in aerodynamics, which is called the potential flow theory. We'll be looking at what a potential flow is, and subsequently we'll also look at what we call elementary flows. We'll be covering one kind of an elementary flow, which is the uniform flow, in this video, and in the subsequent videos we'll be looking at other elementary flows. The whole point of starting with these concepts is that we can build upon these in order to try and explain and model more complicated concepts like thin airfoil theory, etc. So let's start off with potential flows. Potential flows are very simple flows in the sense they are incompressible, they are irrotational, and they are inviscid. So these two are the main assumptions that go into the definition of potential flows. The inviscid assumption might feature more when it comes to determining the pressure from the velocity field through Bernoulli's theorem, where viscous effects do not exist, or rather we don't consider the viscous effects. So from fluid flow theory we know that for an incompressible flow, the continuity equation takes the form divergence of velocity is 0. For an irrotational flow, the curl of velocity is 0. Now, mathematically, if the curl of any vector A is 0, then A can be expressed as the gradient of a scalar function, which is called the potential for that vector. So in our case, since the velocity field, the curl of the velocity field is 0, velocity field can be expressed in terms of the gradient of a potential function phi, which we call the velocity potential. On plugging this equation into the continuity equation, what we get is del dot del phi is equal to 0, which implies del squared phi is equal to 0. As you all know, this is the Laplace equation, and an important property of the Laplace equation is that it is a linear equation, and the significance of that is if I have phi 1, phi 2, so on up to phi n, all satisfying the Laplace equation del squared phi equal to 0, then any linear combination of these solutions, when I say linear combination, I mean something of this form: lambda 1 phi 1 plus lambda 2 phi 2, so on lambda n phi n, where lambda 1, lambda 2 and lambda n are all scalars. So if I take a linear combination of this form, this again will satisfy the Laplace equation. In terms of what we are trying to do, this has a very deep significance. What it means is that if phi 1 is a potential flow and phi 2 is also a potential flow, both satisfying the Laplace equation, then lambda 1 phi 1 plus lambda 2 phi 2 will also satisfy the Laplace equation. Hence, with two flows, we can add them up to get a third flow, and we use precisely this concept to break down complicated flows into a combination or a superposition of simpler flows. Typically, the simpler flows are what we call the elementary flows, and we add up elementary flows in order to get more complicated flows. Before we look at the first elementary flow, I would also like to highlight that for a potential flow, the governing equation del squared phi equal to 0 can also be expressed in terms of the stream function, and that would again be the Laplacian of the stream function is equal to 0. This is a pretty straightforward exercise. If you try to plug in the definition of the stream function into the definition of an irrotational flow. So I can leave this as an exercise for the viewers, but if you have any difficulty, you can always get back to me on this. So now let's look at the first elementary flow. The first elementary flow is called the uniform flow. The uniform flow is a very simple flow which looks something like this. So the flow velocity is in one direction. Let's choose our axes to be x and y. So the x component of the velocity u is equal to v infinity, and the y component of the velocity v is 0, right? So from our definition of velocity potential, that is velocity is gradient of phi, we can get the relation between the phi and the individual components of the velocity. So v is nothing but ui cap plus vj cap, and del phi or gradient of phi is dou phi dou x I cap plus dou phi dou y j cap. So equating the components individually, what we get is dou phi dou x is u and dou phi dou y is v, right? So in our specific case, u is equal to v infinity, v is equal to 0. So we get dou phi by dou x is equal to v infinity, and dou phi by dou y is equal to 0. So on integrating the first equation, dou phi by dou x equal to v infinity, what we get is phi is equal to v infinity x plus a function of y, and that's because this is a partial derivative, dou phi by dou x. Similarly, on integrating the second equation, we get phi is equal to function of x. Of course, we have an arbitrary constant in both cases, but we choose to ignore them because in most cases we talk about the derivatives of phi, in which case the constants would vanish. So just combining these two, what we get is phi is equal to v infinity x. So for the uniform flow, phi is v infinity x. You can also see from here that if you take the Laplacian of this equation, you end up satisfying the governing equation del squared phi equal to 0. Along similar lines, you can also derive the stream function, and that again I would like to leave it to the viewers. I'll probably give the formulae that would be required to do that. So what you would need is dou psi by dou y is equal to u, and dou psi by dou x is equal to minus v. So using this, you can find the stream function for the uniform flow. So that's about it. So we will be looking at other elementary flows in the subsequent videos, and also we will see how combining different flows, different elementary flows, can give us meaningful flows, more physical flows that we generally encounter. So thanks for watching. Stay tuned for the next video. Thank you.